Okay, welcome everybody to the second colloquium talk today by Amir Vaxman. Dr. Vaxman is an assistant professor at the Department of Information and Computing Sciences at Utrecht University. He earned his PhD in computer science from Technion in Israel in 2011. And before his position in Utrecht University, he was a postdoctoral fellow in Technical University of Vienna at the Geometric Modeling and Industrial Geometry Group, where he also received the Lise Meitner Fellowship. His research interests are geometry processing and discrete differential geometry, focusing on directional field design, unconventional meshes, constrained shape spaces, architectural geometry, and medical applications. He served as a program and general chair of the Symposium on Geometry Processing, as well as an associate editor of IEEE Transactions on Visualization and Computer Graphics and the Visual Computer. We welcome Dr. Vaxman to talk about exploiting structure in directional field processing. The floor is yours.
Thanks, Albert, for the introduction. And I'm going to talk about some of my recent works in one of my favorite subjects, directional field processing. So without further ado, let's begin. Spoilers. First, I want to either define or reintroduce what are digital directional fields. Essentially, if you have some geometric domain, usually something like a triangle mesh or some image in the plane with pixels and so forth, something volumetric, then a directional field is simply put, to every point you assign a vector, or not just one, a collection of vectors. The variants of what we call directional fields are, first of all, indeed a single vector field, which is something that we all know more or less in several usages. It's, for instance, winds in climate analysis or blood flow in medical imaging. Then there is something called a line field, where you do care about a vector, but not its specific sign. It can be forward or backward, and it indicates some kind of alignment, a direction of flow, that, for instance, can be used in directing alignments in architectural design. You see those nice stripes on this building, or printing directions in fabrication. And then you can take it as a general purpose to n fields, n being the order of the symmetry. So for instance, if you see in the image above, there's something we call a cross field. There's 4 symmetry. You can take it into 3D, and then there is what we call octahedral symmetry, 6 directions like a cube. This is, for the most part, used for meshing. We use those crosses to direct where quadrilateral will be when we want to turn meshes into quadrilateral meshes, or like you see in this image, hexagonal meshes, where every face is a cube. So for a lot of part, and most of what I will discuss in this lecture, are what's called tangent field on surfaces. So you have this kind of surface. The surface has a normal, a direction which is, every point you stand is up, and the vector field is always orthogonal to it. So the vector field is always on the surface, leading to somewhere else in the surface. So there's a single vector field, which you can look at it like this. You also already see some kind of properties of the vector field here. There's some kind of trend, a vortex going around this red point, but indeed it's still something discrete. You don't see a vector in each point. You see a vector here in each triangle or some other object that is discrete. And then you can generalize it what we call 2 rosy or rotational symmetry field, where you have 2 directions that are differ by rotation of pi, or those 4 rotational symmetry fields, those cross fields. What do we use them for? And this is like an entry point to my talk about how I play with this concept, deconstruct it, make it better a little bit. I will take one pipeline that is common, and it's called the meshing pipeline. So it begins from left to right. On the left, you have some original mesh. It's usually like a triangle mesh. It has to be nice, watertight, no noise, no problems. You identify some kind of features. Those features, you want them to be line in the final mesh on the right. And then you say, okay, let me compute some kind of cross field. That's the second image to the left on this kind of thing. The cross field would have those singular points. I will not formally define them, but they are points where the cross field has a defect, like the corner of the cube. And then I'm going to take this cross field and I'm going to integrate it. Integrate it means finding a function that the cross field is like the gradient to this function. So it follows the trend of those vectors. So this is the second from the right image. This is what's called a parametrization. So this is some kind of function, like actual numbers, UV, like texture mapping, such that those blue and those red lines are the isolines of the function, where it is integer. And then we take those lines and we consolidate them, make them into a quadrilateral mesh that respects all the features we wanted to the right. That's a common pipeline. It's used in most of the software like this as is. But this so-called pipeline, which is already classical, has a few shortcomings that I handled and other people have been handling. But let's see what we want from those fields first in order to determine what's the problem exactly. So the desiderata, the things we want. One thing we always want of fields that they would be smooth. Smooth means that if you have two neighboring fields, like you see here, triangles, and those triangles have fields that are near one each other, across an edge of the triangle, you want the difference between them to be minimal. So that's the definition of smooth. What is the problem? If your original domain, in this case the triangle mesh, is very low resolution, then there's so far you can represent. If the field has a lot of rotation and stuff, if you look really deep, like look from afar, you can see this has this kind of magnetic thing going on. The field has some kind of rotation around it, but if you look closely, it looks like noise. There's a big difference between neighboring triangles. So you get artifacts, and the computer cannot always identify the main trend. So you're saying, okay, this is low resolution. If I go high resolution, the problem's solved. Well, of course, high resolution is always a computational problem. But you say, maybe I should have this computational problem, right? Well, not always. A lot of the times, those fields are actually represent some kind of low-dimensional data. For instance, I told you that fields can be like fields of an electric field, a magnetic field, or something of the sort. So let's suppose there's a charge right there where the red part on the nose is. This charge is literally the only piece of information of the field in existence. The rest are just magnetic fields over it. I had to use a really, really high resolution mesh to represent this single piece of information. It's extremely superfluous. So that means I needed for smoothness a lot of oversampling. So between low and high resolution, there is still some kind of difference in what I need. In addition, something else that we want from fields are to respect what's called features of the field. That is also like a problem of low and high resolution. Features are usually things like singularities. Singularities are, simply put, in this kind of field, things where the field goes from, like think electrical charge, which is a plus or minus, depends how you look at it, and then sources, they're minus, and vortices where it goes around, like the magnetic field. And then there is alignments. So if this kind of object has sharp points, then I want my mesh to align to those sharp points, and therefore the field that I'm using to generate the mesh should align to those sharp points. And finally, and very important, because we would need it for computations and a lot of stuff in scientific computing, you want a field that has several specific differential properties. That means you want it to respect things we know, or hopefully we know from calculus. That means, for instance, that if a field is a gradient of some function, then it has what's called curve zero. It doesn't rotate. It looks like this. Imagine the function is from this white to blue. Then the gradient field is going in the steepest ascent location, like in the continuum, and it has to have curve zero. That's just a calculus definition in the discrete setting as well as in the continuous. Otherwise, there's a big difference between discrete and continuous, and that it's not structure preserving. The other way around, if a field is somehow the result of, let's call it a vector charge, this G, like a magnet, then we want it to have divergence zero, like this. This is a field that is the result of a magnet. The field is rotating around. It's like the opposite of curve free. It has divergence zero. It just keeps rotating, but it doesn't change volumes when it moves. I'm sorry I'm not explaining those specific subjects. There's a little bit of calculus that you need to know to understand this, but I hope it's fine. So I'm going to talk about a little bit about what I talked about, discrete gradient curve, just because it appears a little bit later. In a discrete setting, what we use are functions that are called piecewise linear. That means you have a mesh, there's a number on every vertex, and the function is interpolated linearly on the triangle, like colors or textures or stuff like this. And when we talk about its gradient, that means that the gradient is a single vector per face. It's the direction where the function goes up as steep as possible. In this case, you can see that the function is bigger in the middle vertex than some of the vertices on the surrounding of this middle vertex. In this case, we also have that the dot product between both sides of the edge is the same, and this is what we call discrete curve. So this kind of thing is structure preserving. And we oftentimes want to compute frame fields that are curve-free, so we can integrate them into parameterization and then meshes. So we take this nice field that we want to integrate into a mesh. And when we want to have it curve-free, that means there is some kind of matching between the vectors, such that each of those matched vectors are curve-free. But that's enough details just to close up this point. I'm going to talk about one of the, sorry, this screen, yes. One of my recent papers that I did to alleviate the problem between low and high resolution, and that's called subdivision directional field. I did it with one of my master students, Bran Kasper's. The point is, instead of working on something that is only low resolution or high resolution, we work multi-resolution with something called subdivision surfaces that I will soon explain. Okay, and that means I have fields in both like a low resolution and in a domain which is slowly refined and it's high resolution, where the point is to respect all the features of the field, both differentially, like curl and divergence, and topologically. So if something rotates around some point, we want it to rotate both coarsely and finely. Subdivision surfaces on one legs are surfaces where you keep inserting points inside edges, so you refine and refine and refine, look at this golden image, and make it finer and finer and more smooth. They are used a lot for computation because it's like multi-grid. It allows you to compute stuff coarse to fine and then back again, so to solve things in an efficient way. The point of our work is to get structure preservation. That means we could compute something on a coarse mesh, which is fast, and make sure that when we refine it to the fine mesh, it keeps all the properties we liked. All the vortices intact, the curl intact, so something is integrable. That means that if some field is a coarse gradient field and we subdivide it, it's still a gradient field. We can integrate it without worrying that there are going to be some error. And consequently, if some field has some curl, it rotates in a certain way, then when we subdivide it, it keeps having the same rotation. So I'm going to show it in the diagram. Suppose you have some kind of, the upper left function, that is some function that I subdivided to the bottom left function. And suppose I took its gradient. I want to preserve this subdivision. So if the gradient of the top function is like this, and the gradient of the bottom function is like this, and the top left function is subdivided into the bottom one, I want the vector fields to be the same. So our contribution was to create this matrix that does that without having to resort to the left side. It automatically gives you this property. And that was very important. Consequently, if a vector field on the left has a specific curve, that means the rotation between neighboring fields, and when we subdivide it, it retains the same curve. So for instance, if there's a magnet and something rotates around, it keeps rotating around in a fine level. So you didn't lose details, you didn't create any artifacts. So for instance, here is an example. On the left, there is a coarse field, but even if it's coarse, you see some trend where stuff flow around. And we keep subdivided, and you see the trends just getting more and more refined. For instance, somewhere between those two holes, you see there's a vortex, like 4 directions, and the subdivision maintains it. It's very nice. So you can safely work on the coarse level and earn the properties of low resolution in terms of computation and still have a nice fine level. Here's another example with more than one directional vector. You see this weaving. There's 3 direction in every point, like suede or some other fabric that has this kind of thing. And you see when I skip subdivided, it kept keeping those rotation. Between 1 and 2, you almost don't see any difference, although it's 4 times as much triangles. So we tried it indeed on an optimization to create this quad mesh that you see in yellow and black. And when we did our stuff, the left one, the coarse optimized, we got almost 2 orders of magnitude speed instead of working directly on some fine mesh. And those of you who knows a little bit of solving like linear equations, stuff like this, solving things on very, very fine domain is a very difficult task. The details of the error, they go away very, very slow. Usually people use multi-grid. They coarsen to go to a low grid, solve it there, and then go to the fine grid again. This is sort of what we did, and we got a lot of improvement over other methods that usually do what's in the right. Okay, so this was one work that expanded a little bit the possibilities to do with direction field. I want to talk about another, which has even more a little bit applicative favor. Let's talk about an object that a lot of people use both in nature and in industrial. This object is called Chebyshev net. It's a frightening name, but it essentially means those kind of nets, which are also quad meshes. Look, those faces are quads. That their property is that all those edges, those lines between the nodes, have length 1. That means it's inextendable. It's like a net or a piece of cloth or something in architecture that is very densely put together. Like all these examples you see here. And in medical industry, for instance, Chebyshev nets make up stents. So those stents, they are deployable, they inflate a little bit, and then they have fixed length 1, and they sit where they're supposed to sit, and that's it. But this is a computationally difficult problem, how to create those kind of things. And we wanted to revert again to directional fields. So I'm saying again, I want a field that will, if you look at this architectural design, there is a field going down there, there's a flow. So I want a field that has length 1 everywhere. Okay, I could use the previous method, but what is the small problem? I before worked with gradients, curl, blah, blah, all those kind of stuff, what you see here in red. Gradients are not, I cheated a little bit before, gradients don't show me where the surface goes, they show me where there's the highest descent. So it goes against those level lines, those black lines. I cannot design with gradients, I need to design with what's called the primal variables, those blue lines, the one that are tangent, go against the line. But then I don't have those nice differential properties. What do I do? Instead, I have, we designed an alternative way to integrate those lines. Essentially, it kind of means that when you walk on U and then you walk on V again, it's like walking on V and then walking on U again. It closes up to a single quad. That means this vector field is integrable. This is also formally called as a Lie bracket. I won't go into much details, okay? But this is what we designed in this paper. We had a discretization for it, so it was very nice. We could create those nice Chebyshev net and integrate them into those nets. So we could, for instance, simulate those nice structures in architecture. The thing you see here has length 1 anywhere. It's deployable. That means you can create it from a net that is sitting folded and then unfold it to create it. Of course, you have to stitch in several places, those blue points. And for instance, one can design stents from it nicely, even if they have those branching blue points. And more recreational stuff like food packages that are also Chebyshev nets. Those lines have length 1. All right. So those were the two big subjects I want to talk about. I want to also mention 2 things currently in preparation. I mentioned them since in preparation means we're submitting like very, very soon. There was already made works. Both of them I'm doing with my current master students. One of them is our purpose was to design patterns on surfaces that are not those, well, let's call it boring quad meshes, even if it's Chebyshev, and which have some kind of periodicity. We wanted to do something more inventive, more creative. For instance, that architects can use to tile patterns. So we wanted, for instance, to ask the question, can we put Penrose patterns on those kind of surfaces? So Penrose patterns are aperiodic. It's a little bit difficult to do with some vectors that are U and V and flowing. How were we able to do that? So the answer is that those kind of patterns still have an underlying directional field reduction. So Penrose pattern and other stuff of this can be created by generating a set of parallel symmetric lines, like you see in this image to the top left, which we can dualize. That means every one of those intersections of these lines we can make into a small quad, and then that can be created into a Penrose pattern. Since I have a method to create those on the surface, so to create like those, if you see here on the left, those filled with 5 directions, and I can integrate those directions into flow lines, and then I can dualize those, this is in the middle, and then I can dualize them, I can create a Penrose pattern on the surface. This was never done before, and there are interesting stuff that go with those singularities that have like weaving pattern, like a basket that is kind of looking weird. And finally, I want to talk about another work that we do in preparation, okay? And that's also goes into a lot of stuff that is very hot right now in geometric processing. It's called directional field, let's call it in the wild. Now, the underlying problem is that so far I assume they have a triangle mesh, and there's a nice neighbor to the triangle mesh, and I can put a vector in each of those neighbors, and I can compare them. Meshes that you get as input never look like this. You get something from some computer-aided design machine industry. It looks like this hell to the top right. Everything is self-intersecting. The geometry is totally inconsistent. There are holes. Things are not touching. You cannot rely to work with like single vector pair one of those triangles. It's just not a thing. No other algorithm will fail. Instead, what we wanted to do is make something a little bit more robust. So instead of using the actual mesh, what we do is we create some envelope around it using the distance to the mesh. And on that envelope directly, in an implicit way, we design a field that has a little bit of thickness, like you see in the bottom left corner. And on this thickness, we design a field that has both the direction in the layer and across the layers. What we create from it is, if you see in the bottom middle and right, is some kind of still quad mesh, but with a thickness. So it's much more robust than the original mesh. And if we can use it, by the way, as is, this is usually useful for computational fluid design. But if we want a good quad mesh, we can just take one of those middle black lines, carve it out, and have for ourselves a quad mesh without having the original, without having to have the original mesh as nice. So I think for the first time in history, I was actually on time. Okay. Maybe I talked too fast, and therefore I'm done.
Thank you very much. First, a round of applause for our speaker. Okay, so whoever wants to ask a question, you could raise your hand and I can give you the word. You can see the emojis. It's also a nice way of showing the...
Yes.
All right.
Something in the chat, maybe not.
So you can use the raise hand button for asking questions.
Mm-hmm.
Let me ask a more general question.
Yes.
I think was it in the 80s or in the 90s that Hofstetter kind of started publishing on the Penrose patterns and tiles with a couple of books, right? He kind of popularized the theme. Was the area kind of vitalized after that, or did it see a lot of interest, or did it kind of have repercussions there?
Yes, but not in computer science. This has floated towards math and physics because Penrose patterns is like quasi-crystals. Mm-hmm. And let me maybe show one thing that is, I didn't mention the word, okay, because it's very interesting. Those lines that you see, you could treat them as light rays across a crystal. And those intersections are where the light diffracts. And one of the discoveries that were made by a lot of different people, Brown, Seneschal, and so forth, is that those points of where the light diffracts are those vertices of the Penrose pattern. They have this aperiodic pattern.
Okay, that's really interesting.
Yeah, that's nice.
So basically, there is some internal structure in the crystal that corresponds to, the Penrose pattern.
There's literal 5 or 7 symmetry that creates that.
But is it because of the growth process that created the crystal?
Yes, the quasi-crystal, yes.
Yeah, so that means this growth process can be mimicked to create similar patterns.
Exactly.
Eventually.
This is basically kind of what we're doing on the surface, yes. It's called a cut and project. Yeah, you can do it mathematically very easily. You can even do it at home. Yeah, you can create a pattern, and then if you see here in the colors, there's only 3 types of patterns. So you can go and buy one of those yellows, blue, and red, and you can assemble it together.
Yeah, this sounds like a a nice OCD work. You need to procrastinate. You know, you have project deadline coming, and you don't want to work.
I'm not going to make the student do that. Yes.
Yes. Any questions for our speaker? Okay. All right. Then we would like to have one more round of applause and thank the speaker.
Thank you for...
Right. I have, by the way, pasted our Twitter link. So if you want to get informed about the coming colloquia, you can follow us on Twitter. Of course, you're also receiving emails, but you know, feel free to tweet about them so that other people can also join. So this kind of concludes the session. I'll stop recording now.